Section 4.4, we're going to look at some components of things that we've actually done before, but in reference to number bases in general, instead of specifically like the Babylonians and the Mayans, which is where we saw some of these components from today already used back in section 4.2. To start with, we're going to take a look at and remind ourselves about our base 10 number system. So our base 10 number system, what we've been calling the Hindu-Arabic number system in the previous sections, we have 10 numerals. And we've talked about the fact that there is no numeral for the 10. We use the word 10 to refer to a two-digit number involving two numerals, 1 and 0. But we do have 10 numerals in base 10. It's just that it starts at 0 and it ends at 9. So if we were writing out all of our base 10 individual numerals, it would look like this. And once we get to 9, we run out of single digits. And so what we do is we say, okay, well, I need another place value. I need to increase this to a two-digit number. And we take the number that's in the ones place, which would be a 0, or when we put it as a 0, and we put the number 1 in the tens place. And then we keep writing out numbers 1, 1, 1, 2, 1, 3, right, 11, 12, 13, until we get to our biggest two-digit number with a 1 at the beginning, and it's 1, 9. And then after 1, 9, it becomes 2, 0. And eventually we have our largest two-digit number, which is 99. And after 99, we repeat the same process with the three-digit numbers. And we do 100 and so forth. Okay, you're very familiar with this number system. But I want you to think about this number system as we explore these others. Now, there's 3 of them on this screen, in addition to the one I just wrote. And there's nothing special about these 3. They're just examples. So even though I'm choosing to look at base 5, base 7, base 12 with you, you might have a base 8 or a base 3 or a base 15 question in your homework, but the process is all still the same. So we're just establishing a process on these questions. So in any base number system, the base itself that it tells you how many numerals you have. So base 10, we have 10 numerals. So how many numerals are we going to have in base 5? 5 numerals, right? How many are we going to have in base 7? 7. And in base 12? 12. Okay? So it tells you how many numerals you have. Now, what that means is that if it's a smaller base than we have, right, we have base 10, so anything that's smaller than that, we can use the numerals we already have. For example, base 5, we are going to write out our first 5 numerals, 0, 1, 2, 3, and 4. And those are the only numerals in base 5. Okay? What that means is that when I get to 4 in base 5, it's much like getting to a 9 in base 10. We lose the ability to write out the single digits, and we got to go to a two-digit number. And the first two-digit number is always the same. It's a 1 followed by a 0. Now, for the moment, we're just going to write out some symbols. We'll talk more abstractly about what this is really meaning in a moment. But these are the numbers. And we would do 1, 0 all the way up to 1, 4. And at that point, we run out of digits in the ones place because we only have the digits through the number 4. So it would become the number 20. What would be the biggest two-digit number in base 5? 4, 4. Yeah. And you'll hear me say, it's not a big deal if you don't, but you'll hear me always say the individual numbers, at least I do my best to. So I say 4, 4. The reason I say 4, 4 as opposed to 44 is because 40 says 4 tens, and we don't have 4 tens because we're not in base 10. So you're going to keep hearing me say something that sounds kind of funny as I say just the individual digits. That's how I'm going to repeat them.
Wouldn't it be 4, 9?
There's no 9 in base
okay.
5, right? So
wouldn't it just be taking that next set?
But it always goes as high only as the digits we have. So this base 5 only has digits through the number 4. So the biggest two-digit number using those digits would be 4, 4.
Okay.
And after 4, 4, what would come next? 1, 0, 0. And we do it all over again.
Wow, that's kind of confusing.
It is a little confusing. But bear with me, it'll become more comfortable as we go. We'll talk more about what we can visualize it as in a second. Let's do this same sort of thinking process, and we'll do base 7. So base 7 will have how many numerals? 7. So it will go from 0 up through what? 6. 6 is our biggest numeral in base 7. So 6, 6 will be our biggest two-digit numeral. So after 6, 0, we would have, or after 6, excuse me, we'd have 1, 0, right? All the way up to 1, 6. And after 1, 6, we revert again and change it to a two-digit number, 2, 0. And then Trey's already jumped the gun to my biggest two-digit number, which would be 6, 6. And after 6, 6, we'd have our three-digit 1, 0, 0. Okay, so we should be able to do this process no matter what number I give you for a base system. And there are going to be some questions inside of my math lab that will simply ask you to write, say, like the first 10 digits in base 8 or something like that. One caveat that I'll tell you, because I don't remember how it's set up, different systems do different things, is that it may not want you to start at 0. It may actually want you to start at the number 1. If it does, just start at 1 and go up 10 digits from there, whatever. And it's, you know, it's got the ability inside of there for you to decide if you've done it wrong, it'll give you another chance, okay? Okay, any questions on those 3 so far? How is base 12 going to affect us a little bit differently than bases 5 and 7?
Because once you get up to 11, you can write the number 12.
Okay, so the problem is that it's bigger, right, than base 10, whereas the ones we've looked at so far have been smaller than base 10. Do you guys agree? The other problem is that we've only have 10 digits, 0 through 9. But if we're looking at base 12, how many digits are we supposed to have? 12. I need 2 more digits, but I don't have any more numbers because our system only has 10 numbers. So we do something a little different. So we're going to write down first 0 through 9. Now, for those of you who've had, like our number theory book for elementary math stuff, they do something different. So just bear in mind, what this book does is a little bit more typical, actually. So what we're going to do when we run out of digits, which we have now, we've run out of digits because we hit our number 9, is we go to the alphabet, and we go from the beginning on. So the number 10 in base 12 is going to be the letter A. And the number 11, because we have to 11 digits, is going to be the number B. So anytime you see the number A in one of these, it's going to represent a value of 10. Anytime you see the number B, it's going to the letter B, but we're representing it like a number. It's going to be the number 11. And we could keep going, right? If we needed to go higher, like we were looking at something like base 16 or base, 14, we could keep going with our alphabet. We just keep taking the numbers sequentially.
What if you run out of letters?
We're not going to deal with anything that big, so we won't run out of letters. Good question. Same question. Yeah. We're not going to run out of any of letters, so you're not going to, what that tells you is you're not going to have anything bigger than a base 36, right? Truthfully, you're not going to have anything bigger. I don't think anything shows up besides base 16. 16 is a pretty good cap. 16 shows up, and the reason is because base 16 is used with computer programming just like base 2 is. So base 16 is called hexadecimal. So 16 is kind of a cap on our discussion or thinking about some of these processes because of that. We see that happening. But in theory, could we go higher? Certainly we could.
So in theory, what would we switch to then after that?
I don't know. They probably would switch to another alphabet, like the Greek alphabet or something like that would be my guess if you had to go any higher, but I haven't seen anything done that way. Double letters is a problem. You can't use double letters because it would be 2 place values, just like when we write the number 11, we mean 1, 1, and 1, 10. So we can't duplicate letters. That's not going to work. It would have to be something different. So my guess is that they would go to another alphabet.
Okay.
Okay, let's write a few more out. After the B, it would do the same thing that the other systems have done. When you cap out your single digits, it becomes a 2-digit number. Smallest 2-digit number is always going to be 1, 0. What would I keep going to after 1, 9? 1A. And then 1B. And then what would happen? 2, 0. So we can continue this process. What would be the biggest two-digit number in base 12?
9.
Nope. BB. So if B is the largest value in the system, which it is, then duplicating it gives you the biggest two-digit number or three-digit number or whatever you would want to after that. And of course, after BB, we would have 1, 0, 0 and continue if we wished. So there's several things that are going to be asked of you in this section. One of them is going to be to list some numbers out. Okay. The second thing that could be asked of you in this section of material is to find the number that comes either before or after, or more likely both, of a given number. So instead of writing all of them out, they're just giving you one number and you go one before and one after. And as they do that, typically they choose numbers where one of the numbers, the before or the after, is easy. And the other number is the tricky one. Okay? So if you think about the number, because we've already looked at base 5 a little bit, if you think about the number 1, 4, I'd like to give you a concrete picture in base 5 because it works nicely to do this. So imagine that you have 3 coins, 3 types of coins. We have pennies, and pennies, of course, are worth 1 cent. We have nickels. Nickels are worth 5 cents, and we have quarters. And those are the only coins that we're thinking about for this to work, okay? Pennies, nickels, and quarters, 25 cents. And somebody gives you a pile of coins, right? What you typically like to do when you're counting coins and so forth is you like to have the fewest coins possible. I don't know about you, but I don't want to carry a bunch of coins in my pocket. And so we tend to not have, like 6 pennies, because I don't need 6 pennies. 6 pennies is the same as a nickel and 1 penny. So I would sort of trade them in for a nickel and 1 penny. Okay, everybody good so far? So with that picture in your mind, let's look back at our base 5 number system. Base 5 number system, I would have 0 pennies, 1 penny, 2 pennies, 3 pennies, 4 pennies. And once I get to 5 pennies, I trade it in for a nickel. So I have a 1, 0. And in a two-digit number, the tens place is now the fives place. That represents the number of nickels. So 1, 0 is 1 nickel and 0 pennies. And then I have 1 nickel and 1 penny and 1 nickel and 2 pennies on up until I get to 1 nickel and 4 pennies. And then I have the 1 nickel and 5 pennies, and I trade them into 2 nickels and 0 pennies. Can you picture it?
But couldn't you just switch it to 1 dime?
We're not working with dimes if we're working in base 5. We only have coins that have denominations or powers that are base 5s. Okay? So we're ignoring the fact that we have dimes in order to establish the picture. I get that. But if we only had the pennies, the nickels, and the quarters, we would have this picture.
So then quarters would be in the hundreds place?
Yes, the quarters would be a 3-digit number, and it would be the 3rd digit over. So when we're looking at the number 1, 4, we actually have a picture that works for this. And we're thinking about this with quarters and nickels and dimes because we have a picture of them, and we can use them. But the same idea works no matter what base system you're working in. You just regroup when you get something bigger than the base that you're with. So we'll talk a little bit more about the regrouping in a moment, but if you think about the number 1, 4, we actually have a whole long list over here that you could go back and utilize on this one. But I want you to think about it sort of independent of that list, because on the next one we don't have a list for this one. If you have the number 1, 4, one of the numbers is easy to find. Is it the number that's before 1, 4 or the number that's after? Before. What's the number that comes before 1, 4?
13.
Yeah, 1, 3, base 5. So it's easy to take 1, 4 and decrease it by 1. That's really what it is. It's easy to decrease the 4 by 1 and get 3. The tricky one is the one where we have to increase the 4, because if we increase the 4 to a 5, like we normally would, we would have a 5, and there's no 5s in base 5. So what would we have to do? What would come after 1, 4?
2, 0.
It would be 2, 0. So this would be 2, 0, base 5. Because I don't have a 5 in base 5 to make it 1, 5. All right, A, 0, 0. One of them's easy, one of them is tricky. Which is the easy one? Before or the after? Huh? The after is easy. The reason the after is easy is because there's a 0 in the ones place, so it's easy to increase that by 1, right? The reason it wasn't easy before is because I had a 4 in the ones place, and increasing it by 1 gave me some value I don't have. So what comes after A00? A01, base 12. So this is the after. So I'd like for you to think about the number before by thinking about what we do in our number system. So I'm going to make up just a random number in our number system. I'm just going to use the number 500. So I'm trying to make it look a little bit like the A00, so that's got the zeros on the end, but I don't really care what the number is at the beginning to make my argument. What comes before 500 in our number system? 499. And let's examine what we did to get 499. Well, the 5 became 1 less. Agree? Yep. And in the ones place and the tens place, I used the biggest digit existing in my number system, 9s. Yeah? So we do the same thing in this base. I need a number that's 1 smaller, right, 5 to 4, than A. What comes before A? 9. 9 always will come before A, no matter what number system we're working in. This is base 12. I could scoop it over just a little bit. And then the 99 that I got for 499 are the largest values that exist in base 10. So what are the largest values that exist in base 12?
Same thing.
B. B, right? The largest value in base 12 is 11, and 11 is represented by the letter B. So I have a B and a B. Yes, Trey?
I was gonna ask you if there would be 2 B's. Why are there 2 again?
Because I've got a 3-digit number.
Oh, so there's 3 digits, it's gonna be 2 again.
There's an exception to that, right? Like if I had been looking at the number 100 and I decreased my 1 to a 0, and then these were the 9s at the end, I could go from a 3-digit number down to a 2-digit number. But only if the number is the 1 at the beginning would that happen. Otherwise, the number of digits would remain the same. Okay, so this process works the same every time, but it feels a little bit funny. I would encourage you, as you're working with different examples, to think, okay, what's a really similar example in my system that I understand really well, and what do I really do? Right? I really, like with this one, the 500 to the 499, decrease the first one by 1 and make the last 2 digits the biggest number in our system.
I
Yep,
think
Jonah.
you said this at the start, so we aren't actually counting to 100. We are counting to, in this case, like 499
So,
or something like that. We're not actually counting to 100 though.
so it depends on what we're being asked to do. But I think that what you're describing, you'll see more of the details of it in the next set of problems.
Okay.
So ask me again if I'm not right about how you're thinking about your question or your statement. But let's take a look at the next set of questions so that we can establish a little bit more of that kind of concreteness of what's happening.
Okay.
Because these are before and afters. Okay, the other 2 things that we're going to do with these numbers, generally speaking, is transfer both into base 10 and out of base 10. Now we've done this before. We did it with the Mayans and we did it with the Babylonians. And we did it by multiplying by whatever place value things were in or dividing by place values. So what you'll remember is we put like powers of 60. 60 squared, 60 cubed. And then we did something kind of similar with the Mayans with some 20 powers in there with the weird 18 thing, I know. And then when we did it the other direction, we did division, and we did that division scaffolding that looks like the top hat, right? So those are the next 2 types of problems we're going to take a look at. This first one is going to be asking us to take a base whatever, the first one's base 2 number, and turn it back into base 10. Okay? A base whatever number and turn it back into base 10. So anytime you're doing these problems, the key is multiplication. And usually when people do it wrong, they switch which they're doing multiplication and which they're doing division on. So make sure you got the right operation. Anytime you're going from base whatever into base 10, which is what we're doing here, it's multiplication. So far, so good. So multiplication by what? Well, we looked at this before. We talked about the fact that this is a 4-digit number. And it's a 4-digit number in base 2. So I'm going to write this out a little bit bigger so I have more space to work with it. And it's all powers of 2. So technically, I start on the right with 2 to the 0, 2 to the 1, 2 squared, and 2 cubed. And if you wish to write 2 to the 0, you certainly can, or 2 to the 1, you certainly can. But another way to think about it is that the right-hand place is always the ones place, just like it is for us. And the second place value is always the base. Ours is base 10, so it's worth 10. This is base 2, so it's worth 2. So if you want to avoid writing out the 2 to the 0, 2 to the 1, which is how I will do it from here on forward, it's always the ones place and the base that we're in, base 2's place. After that, we have powers. So I do need to know, what is 2 squared? 4. And what is 2 cubed? 8. So we need to know what those powers are. So the first way, you'll notice the directions actually ask you to do 2 things. I'm going to do both problems with the sort of part A of the direction set here because it mirrors what we've done before in the past. It's going to feel more familiar. And then I'll show you this whole calculator shortcut business that it talks about. Personally, don't like the calculator shortcut. I think it hides what's really going on, a little bit of a masking of things. It's not hard, but there's no way for me to select the problems without sometimes selecting problems that also ask you part B, do the calculator shortcut. So in order for that problem to now make sense, I've got to show you the calculator shortcut. Okay, so what we're going to do is we're going to multiply each value by its place that it's in. So my value of 1 is in the 8's place. My value of 0 is in the 4's place. My value of 1 is in the 2's place. And my last value of 1 is in the 1's place. This is what we did with Babylonians and Mayans. We multiplied the symbols, whatever the symbols were added together and so forth, times the place value. I'll be a little bit, more maybe clear than is necessary. 1 times 8 is 8. 0 times 4 is 4. 2 times 1 is 2. And 1 times 1 is 1. So I have 8 plus 0 plus 2 plus 1, which gives me 11. If the number does not have a subscript next to it, right, like my 11 in my box, it's understood to be base 10. So if you're trying to give me some number that's not base 10, you need to specify the subscript. Okay, but if it's not specified, it's understood to be base 10. I mentioned hexadecimal before, base 16. That's what we see happening in problem number 2. We've got a base 16 number. So we see A, B, C, D. Base 16 would need how many digits? 16. It would have to go up to whatever the value of 15 is worth, right? So whatever base we're in has that many digits, right? Base 10, we have 10 digits. Base 7, we had 7 digits. Base 16, we have 16 digits. 10 of them are the numbers 0 through 9, which means we need 6 more. In alphabetical order, we've got A, B, C, D, E, and F. So base 16 would go all the way up to F. Okay? So we need 16 digits. So let's take a look then at doing this same process with base 16. So I'm going to write out my horizontal little kind of placeholder lines. My values are A, B, C, and D. But obviously multiplying by A and multiplying by B and C and D doesn't make sense. What is A worth? 10. So this is equivalent to putting a 10 here. If you want to write it as a 10 instead of an A, go for it. I'll just write it above. What's the value B worth? C? And D? 13. Okay, that's just the A, B, C, D. That's what they're worth. And then underneath, I'm going to write the powers of 16. So this is always the ones place, and this is always the 16s, or the whatever place value we're working with place. And then I have powers. I have 16 squared and 16 cubed. And if you don't have your calculator with you when you grab your phone for today, that'll be fine. Can't use it on the test, make sure you have your calculator with you. While there will be one that you can use in the computer, it'll be super annoying if you have to.
On this one, you have a 1, but
I did have a 1. I had 2 to the 0, which is equal to 1. Is that one you're talking about?
Yeah, so then why'd you put 1 there and not that?
That's what I was mentioning before. It's always the ones place. I can put 16 to the 0 if I want, but 16 to the 0 equals 1. So whatever place value I'm in, when I put it to the 0 power, it's going to equal 1. So that rightmost place is always going to be the ones place.
Okay.
So it's almost just like I'm shortcutting it because I know it's anything to the 0 power is 1, so it's just always going to be the ones.
Okay.
And the same thing happens the second place. This is 16 to the 1.
Mhm.
Okay, it's always going to be whatever the place value to the 1, so it's always just going to represent the place value itself.
Okay.
All right, 16 squared. Let's find out what that is. 256. And 16 cubed is 4,096. So we're going to be multiplying 10 times 4096, 11 times 256, 12 times 16, and 13 times 1. So 10 times 4096 plus 11 times 256 plus 12 times 16 plus 13 times 1. Many of you probably have calculators where you can just put that straight in all the way across. That's fine. Some of you may not, so I'll do it step by step. But if you don't want to do it step by step, that's fine. So 10 times 4096 would be 40,960. 11 times 256 is 2816. 12 times 16 is 192, and then at the end I have 13. We would add them all together. We get the number 43,981. My preference is this method because it's expanded form, like we talked about in section 4.3, for base 16. Or expanded form on number 3 for base 2. I like that method because it feels more like the things that we've done in the other sections. You ready to see the calculator shortcut part? Okay, promise it's not hard, it sort of hides things. I'll change colors just to differentiate. And I'm going to shrink these and move them a little bit for the same purpose for now. Okay, that wasn't what I wanted to do. Let's try one more time on that one. Okay, so we'll use pink. Okay, what the calculator shortcut does is it takes the first digit first. Okay, well, the first digit in my number 3 number is the number 1. And it multiplies it by whatever place value we're working with. In this case, it's the place value of 2, so 1 times 2. And then it adds the next value in line. That's a 0. It multiplies all of that by the number 2. And it adds the next value here, which is the number 1. Again, multiplies all of that by the number 2. And it adds the last value, which is the number 1. So here's the number in here. It's 1, 0, 1, 1. That's where they're coming from. Okay? Everything else is just times 2s. So let me show you why it actually gives you the same thing. This first number 1 here is actually supposed to be multiplied by 2 cubed, right? It's multiplied by 3 2s. And it still is. It's been multiplied by that 2, this 2, and this 2. It is being multiplied by 3 2s. If I were to distribute this out differently, I would end up with the expanded form that I started with when I did the problem the first time. The 0 should be being multiplied by 2 2s. And it is. It's being multiplied by this 2 and this 2. So it's all in there. It's just a condensed version to put into a calculator. And of course, if you condense it all down, do the multiplication and so forth, you will end up the same value, 11. So what does that look like in my math lab? Well, in my math lab, what they ask you is something like, what is the calculator shortcut input? And they're going to have you write this whole long thing with this parentheses and the times. That's what they're going to have you write out. That's the calculator part that they are going to reference and how you have to do it. So let's show what this would look like on our second example, number 4. We start with the first digit, which is a 10, right? The A is a 10. And my place value is the place value 16. Like, it's the base 16 is what I mean. So my base that I'm working with is 16. So it's 10 times 16. And then I add the next value. Well, the value B is the value 11. And then I multiply all of this by the base I'm in, 16. I add the third digit, C. Now C is 12. I multiply all of that by 16. And then I add my last digit, which is a 13. So again, right, the 10 at the beginning is being multiplied by 16 3 times. 1, 2, 3. It's there. I just don't think it's quite as clear as the other way that we do it in terms of where did it come from? Are all the pieces present? They are, but it's a little bit hidden. And of course, we will still get 43,981. Any questions on that? Okay, so we multiplied to move from base whatever into base 10. Now we're going to do base 10 back into base whatever else it is, and we're going to divide. So this will look like division algorithms that we've seen before. We have the number 11,028. Base 4 is what we're trying to turn it into anyway, into base 4. So I need to know what the place values are in base 4. In particular, what numbers will I be dividing by? Well, I've got the ones place, the fours place, and then I have 4 squared. So I have to do 4 squared. Type it in a calculator if it's a number you aren't familiar with. This one hopefully you know is 16. But we have 16 here. And then I need 4 cubed. Well, 4 cubed is 64. Again, your calculator will tell you if you aren't sure. 4 to the 4th. It's 256. And what I'm doing is I'm going to keep listing them out until I get something that is the biggest thing that goes into 11,000, or maybe something that's too big to go into 11,000, which clues me to stop. So I'm going to keep going for a little bit because the numbers are not close enough yet. 4 to the 5th. That's 1,024. We have 4 to the 6th. That's 4096. I'm running out of space, so let me shift it and make it a little smaller. That's 4096. 4 to the 7th is 16,384. I don't know why I did that white. And that's too big. Why is it too big? Yeah, it's higher than the 11,000 I'm trying to work with, right? So once I either get to the 4,000 and I recognize that, or at least by the time I get to the 4 to the 7th and I see it's too big, I'm done with sort of figuring out what the powers are. And what I'm going to do now is these numbers, in order from greatest to least, are going to be what I divide by. So the greatest number that works is 4,096. And I'm dividing 11,028. So this is almost like imagining that I have 11,028 crayons dumped on the floor. And I want to figure out how many baggies of 4,096 can I make? Okay, well, we divide it into bags of 4,096, and there's going to be some bags, at least one, right, and some left over. So if I divide this 11,028 by the Then I take the number 2 times the 4,096 to get 8,192 that I subtract. My leftovers right now are 2836. And I go down the list. After 4,096, I have 1,024. Okay, so 1,024. That looks like that will go in twice. That's 2,048 when I multiply by 2. Got 788. What will I divide by next? 256. So how many times will 256 go into 788?
3 times.
I think it's actually, is it 3 times?
Yes.
Okay, fantastic. 3. So 3 times 256. Oh, it's 268. I'm sorry. Yeah, it's 768. Leaves 20. Now, it's really tempting, and I commonly see somebody just say, okay, well, look, the next one that goes in is 16, and they move on. You have to represent every division because placeholders of zeros matter, right? If I give you $102 or I give you $12, is it different? Oh yeah, it's a big difference, right? That zero matters. So we want to divide by every place value. So the next value I will divide by is a 64. And I realize it goes in 0 times, and that's okay. We just put a placeholder of 0. We do 0 times 64 is 0, and we still have our leftover 20 present. But that 0 mattered. Now I can go to the 16. 16 will go into 20 once, leaving me with a remainder of 4. What will I divide by next? 4, first 4. Don't forget your power 4, yeah, or your division 4. It goes in 1 time. Once again, I've got a remainder now at the end of 0, and it feels like I should stop because I don't have anything else to do. But every piece has to be divided, right? Like I have to divide with all the powers of 4, and 1 is a power of 4. So I have to end my division always with dividing by 1. Of course, it goes in 0 time, but I need that placeholder. So my answer is this string of numbers, and I don't have to turn it into these symbols like I did with Mayan and Babylonian. I just list the numbers from top to bottom, goes left to right. 2, 2, 3, 0, 1, 1, 0, and I have to write down that I'm in base 4. That looks gigantic on the screen, my goodness. So I want to pause at this point and show you that you should be recognizing a pattern that you probably haven't thought about until I mention it, but that's okay. And we'll check to make sure it holds for our next one. My base 10 number was 11,028. It had 5 digits, right? Base 10 number had 5 digits. How many digits was in my base 4 change over here? 7 digits. It's more, right? Okay. Over here, number 4, ABCD, was 4 digits in base 16. How many digits is it in base 10? Just count. 5, thank you. 5 digits, yeah? My base 2 number at the top had 4 digits, and its base 10 corresponding piece had 2 digits, right? So here's the deal. When the base is bigger, you have fewer digits. And when the base is smaller, you have more. Notice, number 4. 4 digits, big base, with the 5 digits in the smaller base, base 10. Over here, 5 digits in base 10, 11,000, so forth. 7 digits in the smaller base. So it's an inverse relationship. If the base is bigger, I have fewer digits. If the base is smaller, I have more digits. So let's try that. For our last one of this type of example, I have 99,999. We're going to put into base 9. I need to know powers of 9. So the first ones are easy. I've got 1 and I've got 9 and I've got 9 squared, which is 81. Next I need 9 cubed. What's 9 cubed? 729. Then I need 9 to the 4th.
$6,561.
How about 9 to the 5th?
59,049.
And 59,049 is definitely big enough because my number is 99,000. It's only going to go in one time. And again, if you weren't sure, try one more. You'll find the number's way too large. So this is the list of numbers that I will be dividing by. We always start with the biggest value in the list as our first divisor. So 59,049 goes into 99,999, and I already mentioned one time. Okay, so if we subtract, what will we get?
40,950.
Right, 40,950. What will I divide by next?
6,561.
6,561. So this one's going to go in several times. Six, in fact. So 6 times 65, 61 is 39,366. Double check on me. Does that work? Did I multiply everything okay? Okay, need to subtract that. I have 1584 left. What will I divide by? 729. And looks like it goes in twice. That's 1458. Got 126. What will I divide by?
81.
How many times will 81 go in? Just once. So 81 subtracted gives me 45. Then I divide by 9. Goes in 5 times. I have a remainder of 0. Am I done? Nope. I always have to divide by all of the powers of 9, including the power that gives me 1, like 9 to the 0. Of course, that goes in 0 times. I have nothing left for it to go into. And this is my solution set. 162,150, base 9. There is a calculator shortcut for these. The questions don't actually force me to have to show you. If you want to learn it, it's fine. It's not going to hurt my feelings. I just don't have to because it's not necessary. This works really well, and it's very intuitive where all the numbers are coming from. Okay, so we're using division when we turn things into another base. Now, there are 3 more types of problems. Sorry, I forgot to delete that from the other one. 3 more problems. They're all the same type. What I'd like for you to notice in all of them is that they take bases into other bases that are not base 10. Right, this one goes 5 to 7, this one goes 2 to 8, this one actually puts things in order based on their bases. All these problems result in us having to still turn things into base 10. So these 2 in particular, 7 and 8, what we're going to be doing is we're going to be moving from whatever base they give us, in this case 5, into base 10, which we know how to do because we've done examples. And then we're going to move from base 10 into whatever base we're working towards as our final answer, 7, because we've already learned how to do that too. So this is just 2 steps we've already done in other problems compiled into one problem. Right? There's no need to reinvent the wheel when we can just use the same wheel twice. So moving things from base 5 into base 10 is a multiplication problem. And anytime you move base 10 into something else, it's a division problem. So make sure you're identifying those correctly in the right order. So we have the 4 and the 3, and we're in base 5. So in base 5, we have the 1's place and the 5's place. And we're multiplying. So I have 4 times 5 plus 3 times 1. If we think back to my nickels and so forth, this is saying I have 4 nickels, that's 20 cents, and 3 pennies. 20 plus 3, I have 23 cents. So inside of base 10, this number is 23. So what we've done is we've taken 43 base 5, and we've changed it into 23 in base 10. And now I've got to turn 23 into a base 7 number. Okay, that means I need to know powers of 7. Well, there's the 1's place, there's the 7's place, and then I have 7 squared, which is 49, and bigger than 23. So I don't need the 7 squared or the 49's place. So I'm using division with the numbers 1 and 7. So I take 7 and divide it into 23. How many times will 7 go into 23? 3 times. 3 times 7 is 21. And we subtract. 23 minus 21 is 2. I'll divide by the number 1, leaving me with a 2. And my value here at the end is my answer, 2, 3, base 7.
Wait, isn't that 3, 2?
Oh, I wrote it wrong. I'm so
Oh,
sorry.
okay.
I just wrote it backwards. You're right. Sorry, 3, 2, base 7. Yes, it is, top to bottom. So sorry. So it's going to not tell you, turn it into base 10 first. It's not going to tell you that. You have to know that, right? You've got an example so far, one of them, and I'll do the recording that will have this other example here in a moment of what you do for the other. I mean, it's the same thing. But there's always this intermediate step in order to get there that's to go through base 10. So we take the one base, turn it into base 10, and then we take the base 10 number and turn it into whatever base we're moving into. Any questions on that? All right.